To clean a transducer used externally on intact skin, begin by disconnecting the transducer from the ultrasound system. Dampen a clean gauze pad with water and wipe the transducer, cable, and connector to remove gel or particles. Use a compatible disinfectant wipe to complete cleaning. To perform a high-level disinfection of the transducer, take care to keep the cable strain relief and connector of the transducer dry while immersing the transducer in an approved disinfectant. You can submerge the transducer up to the level indicated on the diagram. To ensure your transducers are submergible, look for the IPX8 designation on the label located on the transducer connector. Do not submerge a transducer without this designation. Caution: leaving the transducer in the solution longer than suggested by the manufacturer may result in damage. After cleaning or disinfecting, use a clean cloth to dry the transducer and store appropriately. Do not use a spray-type disinfectant, as the pressure may force the cleaner under the lens and into the transducer casing.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Smaller piezoelectric elements vibrating relatively faster generates higher frequencies. Larger piezoelectric elements vibrating relatively slower will create lower frequencies. Several parameters affect the clarity of an ultrasound image. One of them is frequency. Lower frequencies are less attenuated and provide better penetration, which is good for deeper structures. Higher frequencies provide better resolution for shallow structures. For optimal imaging, it's critical to select the transducer with the right frequency for the anatomy being examined.
Has over 9,000 elements. The exact number is 9,212. I often get asked why we need so many. We need all of these elements for the three-dimensional acoustic beam forming that allows the X61 to steer and focus throughout the entire field of view. Let's first look at why. A conventional one-dimensional transducer has a fixed aperture and a fixed lens. We want to image in a single plane, but the aperture and lens provide an elevation beam pattern like this. We get good elevation focus or slice thickness over a limited range, with increased clutter and haze in the near field and far field. A 1D array can steer and focus within its single imaging plane, but it can't scan a three-dimensional field of view. It can't steer in the elevation direction. Some so-called matrix transducers provide a few rows of elements in elevation, which provides multiple elevation focal zones and better depth of field. This provides some improvement in slice thickness and focal range, but the improvement is limited by the small number of rows. Also, this type of transducer can't steer in elevation, so it's still imaging only a single plane. In an X-matrix array, the elevation dimension is separated into elements in the same way that it is in azimuth with many rows. Having many rows with independent delay control provides the same degree of electronic control of the acoustic beam in elevation as there is in azimuth. We can focus the beam over a much larger focal length, resulting in good slice thickness everywhere. We can also use this electronic control of elevation to steer the acoustic beam throughout the entire three-dimensional field of view. This provides novel modes such as X-plane with two planes displayed simultaneously in real time, as well as 3D.
بسم الله الرحمن الرحيم. سنتحدث اليوم عن مشاكل التصوير الثلاثي الأبعاد. بداية عند التصوير بطريقة منتظمة، عندما تكون يدنا بسرعة منتظمة سيكون الوضع على الشكل التالي. إذا شكل واضح للمكان المصور. ماذا لو كانت سرعة اليد أعلى من المطلوب؟ نلاحظ تضيق أو أن الصورة مضغوطة. ماذا لو كان السرعة أقل من المطلوب؟ نلاحظ أن الصورة تمددت على الشكل الحقيقي. ماذا لو تنفس المريض خلال عملية التصوير؟ هذه هي أهم المشاكل التي نتعرض لها عند التصوير ببروب الثلاثي الأبعاد. وشكرا لكم.
GE's C-Sound software beamforming platform was introduced in 2015. and with its design around a local big data channel memory, provided excellent flexibility and image quality. Our breakthrough software beamformer platform has now, in our Imaging Elevated release, evolved into C-Sound 2.0. This technology continues to enable the development of powerful new algorithms and innovations in combination with state-of-the-art professional graphics processors offering increased processing power. C-Sound 2.0 elevates image quality and 4D volume rates to a new level by combining these new algorithms and the increased processing power to introduce new breakthroughs. VMAX. GE's C-Sound software beamforming platform, introduced in 2015, offered excellent 4D image quality with compromised volume rates and temporal and spatial resolution at large volumes. With the Imaging Elevated release, C-Sound 2.0 with VMAX enables ultra-high volume rates at large volumes with high spatial resolution, as seen in this example of a mitral valve. The C-Sound 2.0 high volume rate is captured along with high image resolution and a large volume size. For C-Sound, the image resolution as well as the volume rate had to be compromised to obtain a large volume size, while C-Sound 2.0 offers an uncompromised combination of volume rate, resolution, and volume size. In order to increase resolution with C-Sound, the volume size had to be reduced to a keyhole view. Imaging Elevated with C-Sound 2.0 maintains uncompromised imaging resolution of large volumes with high volume rates. The benefits are better structure visualization with larger volumes, better diagnostic imaging with high heart rates, better patient outcomes, faster with no multi-beat acquisition necessary, faster procedures with potential reduction in image acquisition time.
Has a number of elements aligned in a row, and these elements are excited in groups and echoes detected one at a time to form the lines of an image, perhaps 100 or 200 lines that make up a B-mode image. And the plane of this image is defined by the direction that the transducer is pointing in, and if we want to change that plane, we have to move the transducer either with our hand or with a motor in some transducer probes. The X61 is quite different. It doesn't have a line of elements, it has a two-dimensional array of elements. And although the area of the footprint of the transducer is comparable to that of a conventional abdominal transducer, there are a great deal more elements there, not 100 or 200, but 9,000 elements in the case of the X61. And I think you can see immediately that such a transducer, if one had control of all of those elements, could be used in many different modes. One of them is in a conventional beam mode, but also, of course, because you can steer the beam in the elevation direction, that beam mode can be translated without moving the transducer, and indeed you can make two or many more simultaneous real-time beam mode images of adjacent slices. The transducer can also image in the orthogonal direction, and once again it can do that simultaneously with imaging in the long axis direction. And this simultaneous orthogonal imaging, where two B-mode planes at right angles to each other are presented together in real time, is one of the fundamental modes of imaging that the IU-22 provides with the X61 for abdomen and OBGYN applications, and it's called X-plane imaging. Finally, the transducer can be made to sample the entire volume that's available to it, and it's quite a big volume because it's a wide transducer. It can scan up to more than 100 degrees, and these volumes of data can be acquired and processed in real time. Transducer that constitutes this advance, because even if you've got 9,000 element transducer, how are you going to connect it to an ultrasound machine? You can't make a cable with 9,000 wires inside it. And really the enabling technology that has allowed this development to take place is that of the beamformer, the 9,000 channel beamformer, which is not in the ultrasound system but in the probe itself. So those 9,000 elements are connected to integrated circuits which then form the beam and send through a similar wire to the ultrasound system sets of data which correspond to the commands given to it by the host system. So when you scan with an X61, you're literally holding a 9,000 channel modes and begin with an ordinary B mode scan. And if we were to use a conventional transducer, we're always faced with the fixed elevation focus. The slice thickness is at a minimum level at the elevation focus, then gets fatter towards the transducer and continues to get fatter beyond the focus of the elevation. This is fixed by the lens of the transducer. But with the X matrix, the thickness of the plane is determined and controlled by the beamformer itself. And so extremely uniform images can be made which show contrast resolution to those with which we're familiar with a 1D transducer. But if we look at this gallbladder, for example, with the X61, we can also go immediately into a real-time mode, the X-plane mode, and see two orthogonal views of the organ simultaneously. Here a long axis and a short axis, and here, just by moving the transducer, two orthogonal long axes. So that's X-plane imaging. And we can also use the transducer to acquire all of the data. And again, this can be done live or in a snapshot. And this enables us not just to produce two orthogonal planes, but to produce, to reconstruct, in fact, a plane that we never see with conventional ultrasound imaging, the C-plane, the plane that's at constant depth from the transducer, the one that's orthogonal to the two right-angle B-mode planes we can obtain by rotating a conventional transducer, or live using the X61 in X-plane mode. And here you can see the two X-planes with the C-plane below it. And of course, if we take those three orthogonal planes, all kinds of processing are available to us. QLab does this on board the system, and this particular depiction of the biliary tree is made by inverting the echo-free areas and then rendering them, so we get a kind of a virtual view of the three-dimensional branching structure of the biliary tree. There are many other things that can be done with the X61. One of them is to, instead of making a very uniform thin slice, to make a uniform but slightly thicker slice. And this so-called elevation compounding or thick slice imaging reduces speckle and increases contrast resolution, allowing you to see with better clarity structures of near equal echogenicity. So thick slice imaging is available to enhance contrast resolution. Very thin slice imaging gives the highest spatial resolution, and the ability to vary these is uniquely associated with a matrix array. So in summary then, I've just gone over some of the basic properties of these arrays. It's a new level of precision basically in the positioning of ultrasound beams in tissue. And these are done with the IU-22 to provide thin slice B-mode images, simultaneous orthogonal plane or X-plane imaging, which of course is a live mode, multiple plane imaging as well, including C-mode images, which can also be made live, 3D visualization, and this includes both the ability to show surfaces, as I gave an example of, but also MIP imaging, that's maximum intensity projection imaging, where we visualize an entire structure and see through it, and this may have some applications in the abdomen and gynae areas. We can do elevation compounding, which reduces speckle and improves contrast resolution, and Doppler and contrast modes are already available on this. And I think, above all, this new technology gives us a glimpse into what the future of ultrasound is going to be like, where